Hello everybody, and welcome to another awesome Rebel Way tutorial. This time we're going to be taking a look at how to recreate this One Punch Man effect that you're seeing on the screen now. Obviously, One Punch Man is an anime. I'm always saying how anime is the best source of inspiration when it comes to effects, and you can see you can recreate it in a more realistic fashion, but still take all of the principles that they are introducing with anime, which is timing and shapes, speed, scale, everything. We recreated this here. Special thanks to Jesse Gozo. He was so kind enough to help us in the creation of this tutorial. Well, in the end, we're going to be sharing this hip file, which is a more simplified recreation of what Jesse did, and we're also gonna share the setup that Jesse has. His setup has even more workflows, and in some cases they're a bit more advanced, but it's still a very, very good hip file to look into and learn from it. So, all right, let's see how this was done. We actually have a few different elements that are at play here. Let me first give you an overview of how this is going to work. So we have our RBD, and this RBD is actually all fake. Fake in the sense that it's not actually a simulation, which is my preferred way of doing things. If it's unnecessary to do a simulation, if you can avoid doing a simulation, you should always try to avoid it. And in this setup, we're going to be taking a look at some of the very cool things that you can do with primintrinsic attributes and animating the transform attribute using some code. I know it looks intimidating, especially for somebody who is new to this. I'm going to go step by step, explain all of this in greater detail and how everything works, because this is something you almost need to understand when you're dealing with Houdini, and if you want to take your Houdini effects to the next level, because this applies to many other areas in CG, especially in Houdini. So we're going to be taking a look at this setup. We're going to be doing some secondary RBD elements, like these elements, and you can see I was just copy pasting a simple a platonic geometry here, even though from this distance you can hardly tell what it is. But yeah, this is going to be this setup. We have the center smoke, which is quite simple. And for anybody who's going to be taking a look at Jesse's setup, you will see that he had a more complex setup, and maybe it was a bit more adjustable in some areas, but this works completely fine. So this is just the middle explosion, the spike explosion that happens, and we have the smoke wave that is kind of spreading when the destruction happens along the surface of the planet, or the moon in this example. And then the last one is just the center flight that Saitama, basically it's Saitama just flying through and he's leaving a trail. And this is not even a simulation, it's just a VDB extending like this. So just a geometry VDB with some noise on top. All right, so let's jump in. The way I'm going to be teaching this tutorial is I have a pre-made setup, but anywhere that I feel like I need to offer more explanation, I will reconstruct it from scratch. I think that everybody is going to be able to follow along because you do have the hip file. This is just to make it a bit easier on myself, because we do have a lot to go through in this tutorial, so bear with me. All right. So we have a sphere. We are just creating some point normals, projecting UVs with a polar, and then quick shading it. I have this moon, but this is irrelevant. We're not going to be really using it for anything else. for any of the setup. And so we have our planet here, and we are creating this center point. Now this center point can be created in many different ways. I will show you guys, I'll reconstruct this setup and give you more explanations this is for anybody who is not super familiar with Vex, or for any beginners or intermediate users. I'm going to be re-explaining everything in detail. Anybody who already knows this, I am sorry, but you will have to either skip this or just listen along. So the reason why we're doing this middle point is, yes, we could just go in and select it and just create a group around that and just use it as our middle point. But for the purpose of teaching, I'm going to be doing it the hard way and the long way. The reason we need that middle point is so we can create our mask. So with that middle point, we are then using its position, subtracting it, and creating this mask. The reason we do that is so we can create this wave. So if we quickly visualize what this wave is doing, it's going to be like a pulse. And that pulse will be driving pretty much all of our effects. You will see we're going to be referencing, how did we call it? The wave. We're going to be referencing the wave and the mask center quite a lot. And I only use CD to just quickly visualize attributes. A good practice is to never store your attributes in the CD because it can become a problem later on. All right, so get center. This is get center the hard way. We're doing the near point expression here. And the near point is essentially saying, near point, we're going to create a simple grid here. We'll do more points here. Create a sphere. Lift it a bit. Just going to put it to a polygon. We don't need a lot of points for this. All right, so the near point expression is just going to be saying, look up at the nearest points on this geometry and return them to me so I know which points are they. So if we type this, and I will create an attribute, points equals near point. So we want to look at geometry number 1 and our position. So we're looking at 0, 1, which is the second input because it goes from 0, 1, 2, 3. And we are looking our position and we are returning a point. So if we look at our point, so our point 0, the closest point on the sphere geometry is point 4. So this is returning that information on our geometry. Now, the simplest way to visualize this is by creating a color attribute again. Let's create this, put it to red. And this one, put to black color. And we can now use those points to extract a color. So we're going to say CD equals point 1. We want the color and we want it from these points. So I add BTS. All right. So we're using the point expression. We're looking up what is the color on our sphere. We are taking that color and then we're essentially saying what point had that color. So if this was a random color, you could see that, let's say this is point 1, 2, 3. So all of these points that are the closest here, let's say this is point 3, they're all getting this color that is coming from point 3. So it's essentially raying everything. And you can also see this gives us a Voronoi pattern, which is quite interesting, right? Because that's pretty much how Voronoi works underneath the hood. If we just put it back to a constant value, so all of the points are just getting red now, but we need to limit this. So what we're going to do here, it's always very cool that you can just go into the Houdini help and just read what this is happening. You can see there's a few different ways of using this function. So the way we're using it right now is like this, but we can also use it near point. We can specify the geometry, the vector position, which is the at P, and then a float at distance. And the way we're going to do a difference is just channel, we call it max list. Now let's put this to 2. All right, very cool. So this is giving us is arraying everything, and we're also creating a distance now. Now this is the long way of doing it. The very shorter way of doing it, and how I usually use it, is you can just do a attribute transfer, and you will see something very interesting. Just to 2, we get the same exact result. All right, so that's how the near point works. The way we're using it here is almost like the invert of what we just did, because we only want to know the point number. Oops, where are we? Got lost there for a second. Here we go. We only want to know on our geometry, what is the point on our geometry, and then set that point to red. I know it's way over complicated to get what we are doing here, but for this purpose, I do want to illustrate it. So I'm going to put this to a primitive, just so it's only one point. So we first want to get the position of this point. We're going to say pause, point pause equals 0.1 position and 1.0. Now we are gonna create the same attribute points, call it near point, and we're gonna be looking at on the near points from our geometry based on that P pause that we just grabbed. And not near points, that's for arrays. So near point on our geometry, and look at the position on our sphere. What that will give us is the closest point on our geometry, which is point number 4994. 49. 49. So with that, we can now extrapolate set a color just on this point. But we also don't want to run this through all of the points. We just want to run it as a detail attribute to just get that one point. And what we can do now is set point attribute. And I always forget this one, but it's on ourselves. Let me see. Ourselves, we want to get the CD. We want to set the CD on I at this point. This is our value, and we want to set it. I feel like that's the right one. Yes, it is. Okay, so we're getting that point. That is the closest point. And we are setting it. We're setting this point on to a red color. Okay, and you can see if we move this, it's just going to be raying directly down and grabbing that position, grabbing that point, and now we're setting it. And that's pretty much what we're doing here. I told you it's going to be the long way of doing this, and it's not the best way of doing this, to be honest. You would probably not do this like this in a production environment, but it's good to know why Jesse was doing it exactly this way here. So we were just creating a point, we were transferring it, and then you can see if we move this transfer, it's gonna pick a different position, just like in this example. So I'm gonna put it back. All right, so that's that setup. Now we're just gonna delete and only use this point because we set this to a detail attribute. We can use a detail expression here and just pick that point. So you can see we can either delete that point or keep that point. And you need to type these backticks here in order for this to be evaluated. So if I quickly do it here on the side, last, we're going to say we want to. So this is almost like getting, doing a point, but we're going to do it on detail as a detail attribute. So we want the on our geometry, we want to grab the PTS and it's on 0.0. So this is not going to work. To be on points, this is not going to work because we need to execute it like this, and we're going to say delete everything but. And yeah, it was the NPT here because in this case we were setting this as an NPT. All right, so that works. Another thing that I want to specify here is almost like the inverse of near points is the min pos. And if we have our planet here and we have our sphere, so this is the point that we are otherwise using the near points position on. If I copy it to a sphere just so I can illustrate it and do a min pos, you will see what happens. This is essentially, it will ray itself to the nearest point on a geometry. And again, if we start moving this, it's just going to be doing the same thing as we were doing, on this simple example. But I'm just trying to illustrate how all of these expressions are sometimes doing a very similar thing, but just slightly inverted. Okay, so let's do the mask now. That is going to be a good starting point for all of the other effects that we're going to do. And we'll recreate this here for you guys. So what we want to do is essentially get the position. Get the position from the center. That's why we blasted. And we want to subtract it from all of the other points. And based on that, we want to calculate what is the distance from that subtraction. So first we want to get the, let's say, P position again from our blasted point. So we're going to say 0.1, position on 0.0. Now, let's put this into color where we want to subtract them. So you can either subtract and calculate the length. So we would do length, ppos minus our position. That's one way of doing it. Or you can do a distance, which I prefer doing. And now you just say pos and our position. See, you get the same result. Now this, we do want to fit. So just so we can control it better. So we want to fit this between 0 and a maximum value. So in this case, I'm going to set to 50 because I know the size of the sphere of our moon is max. It's set to 50. So we're going to set it to 50 and we want that to be between 0 and 1. All right, so we have something. In order to control this, I usually set this to a channel. In most cases, max. And That way you can actually see what's happening here when you're refitting it. Put it to 50 for now. And all of this, we want to wrap it in a ramp. So it's easy to control. Just ramps, we usually call them ramps. And just put everything into a ramp like that. And we're going to invert it. So we're pretty much done with our ramp here. Let me see what else I did here. The only other thing is I'm going to be storing this into a max center. So the way you do that is just, so like I said, never store it into color, right? So in this case, we would say float mask. And now we would say mask center equals mask. So, and now you can check it with the color swap. And that's how we get our mask. All right, so this is the mask. All right, so now let's create this directional vector. This is something we're going to be using quite a lot throughout the other setups. You can see everything is pointing inwards or outwards. You can easily invert this vector. We're going to be using it all over the place, like on this debris, just to advect our particles in this kind of way. It's very helpful. Well, actually, we're gonna be using it in all over the place. So let's create one. Go direction. Just gonna make it a bit bigger. Oops. Let's put it to like 4. All right. Let's do another wrangle here. If you remember, we were storing our point NPT here in our detail attribute. So this is the NPT point number. So on our geometry. So we're going to use that. So we're going to bring it back. We're going to say impact point equals detail attribute 0 NP. Sorry, so we need the norm. Yeah, so NPT and on 0. So now we have that on our points. And now we're going to say we need a vector impact normal that we want to get from that point. So 0, normal, and impact point. So now we have that normal from that point on our geometry, and we can visualize it if we put it into, in direction equals that. So you can see what that vector is. Just it's pointing outwards like that. We also want to grab another vector, which is just our normal. Normal equals normalized. We're going to normalize this. And we also want to normalize here. We're going to say this impact normal equals normalize impact normal, just in case. So everything is normalized. All right, so now we're going to do a cross product between those two vectors. Now, cross product is essentially when you have two vectors. I will do my best to illustrate it here. So you have one vector and then another vector. And imagine this is like a grid, well, a single face, a polygon. And which one do we have? Blue. And when you do a cross product, you will essentially say cross product between this vector and this vector, and it will return this vector, which is essentially a 90-degree angle. And if you return the red one and the green one the other direction, it will do it in the other direction. So you get a third vector. And if we do this here, we're going to say cross product between our impact normal and our normal. And this will give us this third vector now that is going to just run in circles. And now if we do this again using this vector, and we do it again with our normal, we're going to get this vector that is kind of running away from everything. You can see it's going away. Did I invert it? Yeah, I inverted it. So in our case, so that's why I was saying if you do it the other way, it's going to invert it. So essentially what we want here, just so we are consistent, we want to invert these two, the normal and this one, and it will go away from us. So if we quickly check again, I will remove this one cross product, and you can see if I check our normals, so this is one vector and the third vector. And the vector that is going to be created now is going to go in this direction. So if we go back, you can see that. And it's going this way. Or if you invert these two, it's going to go in that direction. But for now, I hope this makes sense. All right, so we are setting our direction. We are processing our direction force here. So you can see direction, we normalize it, and we're going to invert it. So if you say -1, it will just negate. It will negate, it's going to do a complement. So if for anybody in that if you want to do in this in VOPs, it's going to do a complement, which is 1 minus x. This is the same thing. And now we are also saying direction. We're putting it into a ramp, and then we are multiplying. Well, we're using that mask center as the ramp. So here is our mask center. And if you can see what that is doing, we are now multiplying everything that is outside. This is pretty much set to 0, but here we still get some strong vectors, and we're going to be removing this back in a second anyway, so it's not that necessary. All right, so let's continue to the anim wave. This is something we're going to be using for a lot of other effects. For instance, here we're going to be creating this line, and this is going to be driving other stuff down the pipeline. So let's see how this is created. We're going to be using something called an absolute function here. And this function literally just returns the positive equivalent, returns the absolute positive equivalent of the number. So here, let's look at this number. It's minus 1.1. If you put it through an absolute, it will become 1. It will just remove the minus, right? It just inverts it like that. So the way we're going to be using that is that we're going to be taking a look at which values are negative. So in this case, only the white values here are negative, and that's why they're going to be inverted into a positive. And that's how we're going to be creating this ring. We're going to be using our trusty mask center, and we're going to create a new attribute called wave mask center. So far, so good. We're going to be pushing this into color just to visualize, and now we're going to be fitting this between 0 and 1 and 0 and 1. Great. So this doesn't do anything yet, but if we start changing our min and max values, you can see we're getting a more sharper edge. So in this case, I will just rename this to thickness. So that will start controlling our thickness. Now, if we create an absolute from our mask center, this won't do anything because our mask center doesn't really have any inverted values right now. By inverted, I mean they don't go into a negative value. If we look at this color, they stop at 0 and they go to 1. It will have, when we start inverting anything into, when we start pushing these values into negative, that's when the absolute starts working. And the best way to do that is to just subtract our values here. And let's subtract it by 0.2. And that immediately works, as you can see. And just based on it's saving the project. So just by changing this value, we are essentially getting that animation, right? Which is kind of, it's very cool. So what we want to do here is create a channel to subtract. So CHF, we're going to call this offset. All right. So you can already see this is creating what we want. And it's stopping where our values are kind of stopping here, right? So if we want to make this bigger, if we want to make this transition go all around the sphere, we would just have to extend our mask, the mask center. But in this case, you can see something starts happening here, and that is because, well, this absolute, like I said, only works when we go into the negative. So right now we're subtracting 0, so we are back to our basic result. But as soon as we start subtracting something, it's going to start negating those values. So what we want to do is float offset. We actually want to clamp this. Create an offset attribute, and we want to clamp this between, I don't know, 0.15 and 1. So we never go to 0 that way. And now instead of this, and let me remove this offset here. Instead of using it here, let's use an offset like that. So you can see we can never go lower. When we are at 0, we're actually at 0.1. So maybe we can do this. So now we can just animate this. We can invert it here like that. This is controlling our thickness. And if we animate it coming from here to here, and we do a very quick, we didn't animate it, right? No. And this is going the wrong direction. Like that. So we quickly animate it. We do it like this, actually. So it, poof, very exploding. And then it has a longer fall off. Like that. So it's pew, super fast and punchy. So that's pretty much how that was made. All right, let's continue. So we have our timings now. We're going to go forward and isolate just that part. In this case, we're just isolating anything that is lower. So everything that is dark, we just want to remove it. Another way of doing this is using a blast. So you can just remove it based on the if that wave is bigger than 0.1, remove the primitives, or is it points? Yes. And that will give us pretty much the same result. In this case, we are dividing this, we are removing shared edges and then computing the ends. So this will essentially just give us this result. So it will remove everything else. See, without the divide, the ends will just give us all the in-between primitives. But here, remove shared edges will remove all the polygons in between. And then we create an ends, a row with shared points, and then a polypath. The reason we do a polypath is you can see now we have a lot of primitives, a lot of polygons. With the polypath, we only have 2 primitives and 2 polygons now. So these are just separate paths. The switch if is just controlling if, don't just remove everything before frame 15. So you can see here, we have nothing because we only have, so only start when frame 15 is activated. And this is a very, like a slick way of doing that. We are here creating our wave ID based on the primnum. So remember, we have 2 primitives. So our primnum is essentially just going between, is just 0 and 1. And we're saying wave ID is primnum. And now with that, we created our wave ID on all the points. So now we can actually separate them. We're smoothing everything because before we had some jagged edges. We're just smoothing, resampling, so we get a lot of points. And then splitting based on that wave ID. So you can now just easily remove one of the points. Yes, you could also just select them. But this is, we're professionals here, so we're doing it the professional way, whatever that means. In this case, we're also raying this guy back to our sphere, because before we were actually a bit offsetted because we were doing the smoothing here, and just so we are perfectly aligned with our moon. We are raying it very simply back, converting it into a polyline just to visualize it, but we're not going to use the polyline for anything. This is the out that we're going to need. All right. In this same setup, I was also creating the smoke that I was showing you in the beginning, that just like a fake smoke trail. And the way we're doing that is just we're fetching that point. If you guys remember from the beginning, this is where we are grabbing that point, fetching it here, putting a line onto it, and we're animating the p-scale because the copy to points is actually recognizing the p-scale attribute. And so we're literally just creating a simple curve like that, and it's just extending it. We are resampling it like so. So we're getting, before we only had 2 points, now we have 1,000 points. We're pushing it through some noise. Now this can be done in a lot of ways. I would usually just, in most cases right now, I'm using attribute noises almost all over the place, putting this to a zero centered, and like that. And that's what I would use here as well. And then you can animate it, the noise, and you can see it's just going to move a bit. So that's what I would do. That's what we did here. We're setting the width attribute. On the resample, we are creating a U attribute. So if we visualize this here, a U attribute is essentially a 0 to 1 attribute that goes from 0 to 1, and that creates a very cool curve that we can now manipulate. You can do a lot of multiplications with this now that it's perfectly between 0 and 1, and you can see it's going to shrink and update with the curve. And that's what we're doing here. We're just creating a width attribute. We're creating a channel ramp based on that curve view attribute that I was just showing you guys. And then we're multiplying with a scale width. This is a global multiplier. And then we're just refitting based on the frame between 21 and 25. And that will create this width. So if we are here, we could actually say start frame and end frame. Right? So now nothing will work. It's not going to get animated. But if we say, so start frame, Just like 22 and 25. Now we will actually get that animation back. And we are again pushing this through 0 to 1 and just CD just to visualize it. And that's pretty much it. I'm doing a switch here again, just so it's not here at all before any of this happens, because you can see it's kind of lingering here in the beginning. And we're just like, yeah, no, just go away. All right, so that's it for the moon setup. So if I do a quick recap of what we did in the moon setup, we created this circle, we created this fake trail, and we created a bunch of masks that we are going to be using on the other setups. We created a directional vector that we're going to be also using that's pointing everything outwards. This is our directional force. We created this very cool animation wave with a bit of overcomplicated methods, but that's okay. And what else? We went through different ways of using the near points attribute, and yeah, I feel like we covered a lot in this section, so let's move on to the RBD section. All right, so here we are at the RBD FX moon. So we are importing our moon again. Let me show you guys what we are actually importing. It's this, the timing layout. After we did the wave, we are importing the moon. So we have that gradient that you can see here. I'm removing that annoying red dot because we don't need it anymore. So it might as well go away. I'm changing so our main mask center, this guy, I'm changing it to, promoting it to a primitive level and changing its name to mask center prim. This is I only need that here because I am splitting based on that mask center prim, like so. And that is just so we get a better, more accurate split. Otherwise it might cause some cracking on the edges if we remove this based on the points. I'm also here creating a down vector, and this is essentially down, down, down. This vector is, oh, this is very confusing. They're just the normals, all right? Literally normalized normals, they're called down right now, and we will use that very soon. All right, so after the split, we have two sides. This is the hollow moon, and this is the side we're going to be doing all the RBD on. I'm poly extruding both because we need the thickness to do the RBD destruction here. Next up, we do a bit of noise, just attribute noise. This is medium-sized noise and very small noise. So we have two levels of noises happening on the position. And we are recording the rest position here. So you can see here in the rest, you get the deforming input, and this is the rest position. So we're going to be taking the position of this guy and recording it into our rest attribute right here. The reason we do that, because here later on, after the Voronoi fracture, we do a very classic kind of trick that we actually do the fracturing on the noised up geometry and then we swap it. That way on our fractures, we get these broken up edges. So it's a very cheap and fast and efficient technique for creating more interesting edges. Obviously you can use a lot of different techniques like the material fracture here, but I feel like this was working completely fine. So now let's do the fractures. Literally just a simple sphere. I'm copying it on itself a few times. As you can see, just because that, and scaling it down, because that will create more points in between. And you will see how that works. Here, I am just using that center point again. If you remember the one we were removing, the one we were isolating here. So our center point. I'm copying everything to that position and raying it back to our moon. So we get this almost like a spider web kind of pattern. And because we have multiple copies here, we get more points that are at a different position, and that will help by with the creating more variety in our fractures. Also, right now, if we look, we add a point deform, and this is exactly where we create those multiple varieties now because we have more copies here. Then we do the fracture. Nothing special on the Voronoi fracture, and all of this I feel is quite self-explanatory up until now. We do the fracture, we do the attribute swap. So this is the attribute swap is exactly like just saying in here, you would say v at p equals v at rest. It does the same thing, but it's in a swap like that. So very convenient. So we already saw that, and we're getting this very cool spider web, shattered glass almost thing. File caching it, naming it. Here we actually do the name, and we don't pack anything yet. We pack it here and just create all the points. So we remove geometry but keep the points. So here we are setting a cluster mask attribute. So this mask cluster is going to be used here later down the line when we're going to be splitting between clusters and non-clusters. Just so you guys know where we're going to be using that. So we assemble everything to get the centroids. We remove the geometry, we use our mask center again to just do like a mask like that, nothing special. And then we set the CD so we can actually see where that mask is going to be. And we copy it back to our original geometry based on the name. That's how the attributes know that they belong to each other. That's how they know where to go on our original points. The only thing that here we had to do is promote the name to a primitive. If you don't do that, there's going to be a mismatch in the attributes. So primitive to points, and now we can rename it back to a primitive. Here we are splitting based on the inside and outside group. So this is the inside group and the outside group. The reason why you would like to do something like that is so you can remesh it. So in this case, we are running a for each loop based on primitives or based on names. So based on a name, so for each named primitive, like so. And if you look at a single pass, it's going to go through each primitive. Let me find a good one, something like that. Then we do a remesh here, and that will just give us geometry that we can use to add more detail to our inside faces. So we merge everything together, and this guy, RBD interior detail, is actually doing that for us. If I do exploded view here, you can see how much detail we have now compared to this. It's very flat. I mean, from this distance, you probably would not notice it, but if you add the RBD detail, you get a lot more. And obviously you can add even more detail, but then it's going to get slower and slower. It's fine in this case because you can then later cache it, but you can see how that works. And there's a very cool visualize noise scale. So you can see that it's only applying the noise based on this mask that is coming from the surface. So I think that's very cool. All right, so if we continue now, this is where we are doing that split based on that mask cluster. So all of the points that were black here are getting in one cluster, and all of the points that were red are coming to the other cluster. And then we're doing an RBD cluster here, if you can check it. And this is just so cluster down. And this is just so some of these pieces are actually kind of connected into bigger clusters. So when we actually do the deformation, they kind of crack open. Some of them, so here, because they're set in a group cluster, they're going to be kind of rotating together, and we can then dial in that rotation later. Instead of all of them being rotated individually, they're rotating in a cluster. Not super important, but it's something that was done here. And then we merge them back together and remove this visualization. And here we're gonna pack everything. We already have the name, so we don't have to do anything else, but we're gonna pack everything. So again, we only get the centroids on our geometry, and we're pushing through the direction, mask center, and down. And remember that direction attribute is everything is coming from here. So set direction attribute. So that's why this setup was quite important, because we're gonna be continuously using all of that. All right, so now we come to this part where it's a bit more difficult to explain, and I will take some more time to guide everybody through this in case you're not familiar with this setup. But I feel like it's very important to know this, and it's going to help you a lot when you're thinking about how the transform works, how some of the matrix things works, and how to use quaternions. So we're actually moving all of this geometry based on their pivots. And we're moving everything with this code. There's nothing else. There's no simulation happening. And you could have done this with a simulation, but this way you have just way more control. So before I dive into this, I actually have a few simpler examples that I wanted to quickly discuss. All right, so let's put down grid. Remove the geometry, keep the points. I'm gonna put down a box, copy to points, geometry points. No, that way. All right, cool. So we have that. So the easiest way to rotate the boxes would be here, but then we don't have individual control. We could use stamping to do some of this heavy lifting for us, but that's not that slick. So what we're going to do here as our first example on how to rotate things is using a normal attribute. So if we say v at n equals, let's just set it for now. And it's a 3 vector axis, 3 floats, and nothing happens. And because it's set to 0, copy to points will know that it's going to be, if we give it a normal attribute, it knows that it's going to be using that to rotate our geometry, our points, and then it's going to rotate our geometry. So if we start changing any of these values, we're going to start changing the rotation on our geometry. All right. But you could just say rand ptnum, and that's going to do a random vector based on the point number. We can also say sample directional uniform. I'm going to say random ptnum as well, and that will give us a random normal based on a point number as well. So you can do a bunch of different things. The easiest one would be to use like an attribute randomize in this case, and just set it to normal. And there we go. And we can rotate our normals. We can go here inside sphere, turn this on, and we can rotate. And this all works nice and fine, but sometimes when you have complex rotations and maybe moving geometries, if you're rotating if this would be a particle simulation and the points would be moving, a normal attribute might give us some problems. So in most cases, you would want to use something called an orient. An orient is a more advanced way of rotating vectors in Houdini, and it's a 4-float vector. So if instead of a n, we put down an orient, see, nothing will happen because we have to set this to a 4th dimension. And you can see orient is a 4-float quaternion. So quaternions are also mathematically more refined rotations that you use in Houdini. I don't want to get too deep into that, but rest assured, if you start Googling quaternions, you will get like proper mathematical papers and equations on how all of that works. All right, so let's get on to more complex examples. I have some ready here on this side. So this is the normal example that we just went through. On this side, we are doing a very simple fracture, coloring it, changing the color here, creating a mask based on the attribute transfer, nothing fancy. I'm transforming this to our primitives and back to our points, because we're going to use it on points. Mask, creating a mask attribute based on our color, deleting our color just so we have this, and then assembling everything and just transferring our mask. We don't need the CD. All right, so now what we want to do is I'm going to put down a transform pieces. Let me create a new branch here. And transform pieces wants the geometry that we want to transform, template points, and the rest points. Since this geometry is not moving, we don't have to do a lot. I'm just going to be creating our points here and deleting. So these are our points, and our rest points are also here. Usually you would have to do a time shift to keep them as your rest points, but because we're not moving, it's fine. All right, and then we have this. So this is acting in a similar way to our copy to points was before, that we're going to be using our centroids here to rotate our main geometry here. So we can do the same thing. We can do an attribute randomize and use the normals again. And that's going to work, right? And we can try the orient. And that is going to work as well. But a more slick way of doing it would be in an attribute wrangle. So what we're going to do here is use those quaternions and rotate based on 2 attributes. So the attributes that we have to create are an axis and an angle. So we're going to create a vector called axis equals, and here we have to specify an axis that we want our points to be rotating around. In this case, I will just create 0 and 1 and 0 just to illustrate. I'm going to create a float called, and we're going to set it to $, just so something is moving forward, so we don't have to animate anything. And now we're going to be specifying a p orient, and that is a quaternion attribute. And you can put in the angle and the axis here. And that will rotate our pieces again. So what we're doing here is rotating on the y-axis. So just on everything pointing upwards, and we are rotating around. So if we look at this here's everything is rotating around our y-axis. Okay, so we have that, and we're using a quaternion, an orient, which is a quaternion, and this will give us much more stable rotations. So what we can do with that is, again, what I was doing there, sample direction uniform, say random num. And now we have random rotations happening here. So that's cool. But what if we didn't want to have everything rotating? Remember, we created that mask and we called it at mask. What we can do is this angle, we can just say, well, just multiply that by our mask. And now everything will be rotating where that mask is reaching, you know, our points. And that's very cool because now we can have even more control happening here. And that's essentially how we are doing the main rotations here. But we're doing another level of complexity here, and that is we are actually rotating directly on the geometry. As you can see, we're not using any copy to points here, or we're not using any quaternions, any transform pieces. Oh, and here's also another good example about even adding more complexity. So let's go step by step. So here it's the same setup, attribute wrangle. Here I'm rotating just on this angle. So rotating just a bit on the angle, and then I'm adding even more complexity. And you can see here the piece is rotating in minus and plus, and I can add position in the P. So that's pretty much what we're doing to our moon as well. So, and the way how this works is we are doing the same quaternion here that we did before. So we have this setup and we're essentially just copy pasting it and plussing it. Okay. So we are plussing it. And that gives us this angle. And the only difference that I'm doing in the angle is I'm fitting it between 0 and 1. And so I'm using the random function, which gives me values between 0 and 1. And then I'm I'm refitting them between -1 and 1. And that's how I'm getting these rotations. Some of them are going in minus, some of them are going in the positive. Otherwise, everything would be rotating like this. But to add even more complexity, you just put it into -1. So now we get this happening here. And now we can also add P, and we say plus equals, and just set it like that. So now everything is going up by 1. But we don't want everything to go up by 1, so we can multiply this by our mask. Everything is going up only where the mask is, where our mask is actually working. So in the middle, more or less. And a cool thing, let's multiply. So now I'm just going to do another float mult equals hy master mult. I know it's a lot of coding in this one. Bear with me. So we do this, and now we want to just multiply the mask separately with this mult. Like so. Let's see if I did anything else. Yeah, the only other thing is I was adding even more complexity to the up and down. So it wasn't just affecting the middle, but it was actually adding some. So fit rand. We add here another fit. Oh yeah, so I was actually multiplying this up here with the mask. So let me just do this, multiply this with mask. So here, if I add this to 1, see everything will go up. And I can even add -1, and some of them will go down. So again, I'm just adding more randomization here. And now I can multiply this with that mult that is already pre-multiplied with the mask. So now, yeah, you can just add 2, or 2, and here 3, and some of them will go down like that. So a lot of control happening here. And the most interesting thing is, if you start moving this, it's going to be moving that mask, and it's going to be moving where our effect is happening on the geometry. So what I was saying before I stumbled across this extra example is that we are not using anything here, any copy to points or transform pieces. We're actually doing this directly on the geometry. And the reason we are able to do that is because we're using something called a primintrinsic attribute, and we are actually using the transform here. So the primintrinsic attributes are attributes that are actually living on our primitives here. Under the intrinsic attributes, you can find them here. They're all hidden. So you can show them all, and you can see it's a bunch of attributes that are kind of written under the hood of Houdini. So Houdini knows where things are, and we can get them and modify them by calling on them with this primintrinsic, and then you set the primintrinsic based on the numbers that you change in the middle. All right, so in this case, we want to use the transform, which means we're going to be changing the transform matrix here and setting some rotation on top of it. You can see we're going to be rotating our matrix twice and then setting it, and that will change the transforms here for us. The simplest way of doing that, a simple form of doing that is here. Actually, I think this one is more simple, where I'm just rotating everything, and you can see there's actually a mistake happening here, which is very interesting. So let's write that from scratch here. So we want to create a matrix called M, and it's going to be, this M matrix is going to be getting the transform values written into this M. So matrix 3, M, or X form, so for transform. Intrinsic, and here I usually forget the order, so I just check it up. So it's on our geometry, intrinsic name, yeah. It's called transform. And we're doing this on the point numbers, or can also be on the prim numbers. Let's see. That's not going to work like that. So, okay, so we have our primintrinsic transform here, and we want to do a bunch of stuff to it. So we're going to again say, I'm going to create that vector axis, and we're just going to do a random based on ptnum. Right now, I'm going to say float angle, so it's the same thing as before, and also set it to time. So now we want to rotate our X form, which is our matrix. Keep me spelling things based on angle and our axis. All right, so nothing happens here because, you know, before we were actually doing this to the orient attribute, but now we don't have that orient. We need to set it. So we're going to say set prim intrinsic, and we're setting on 0, Again, I need to look it up. 0 transform ptnum, and we're setting it. Oh yeah, so we need to set the I completely forgot the transform. All right, so that's actually transforming now. So I forgot the actual matrix, because what we are actually setting this transform, but we need to specify what are we changing to the transform. And we are changing this because we were taking this, we were rotating it, we were rotating our matrix, and now we're setting it here. And based on this matrix, we're changing our transform. All right, so now we have this. The only thing is that these axes are not normalized. So we would have to normalize our vectors. Otherwise, we get some skewing and actually transformation in the, well, actually scaling the geometry, right? And we don't want that. We want our axis to be normal. And again, this can get very complex under the hood. So, all right, so we have our rotation happening here as well now. So everything we did here is what we are doing here when we are transforming this. Even though this feels a bit more complex, but it's actually pretty much the same. All right, so now let's tackle this big chunk of code. I hope it doesn't feel as intimidating as if it did to some of you before. We did in the smaller examples, we pretty much did all of this. We're just gonna add just a bit more complexity here. And we're gonna be adding more documentation about this in the description below if you wanna dive even deeper. All right, so let's tackle this big block of code. It's not actually that big, to be honest. And I'm pretty sure now that we went through all the simple examples, if you're not feeling comfortable before, I hope you at least understand the concept of how this works. We're going to be adding even more documentation about this in the description below if you want to dive deeper. All right, let's do this. Let's try this. I will just copy paste this first line because I don't feel like writing everything. I will make this a bit bigger. All right, so we need to create, we're going to be rotating our matrix twice. So if we look at here, we are rotating it twice. We need to create a random angle, random angle, axis, and there's a random axis here. I feel like I'm going to write it a bit different this time around because I feel it's going to be a bit better. Actually, I'm going to leave it here. Okay, so we need a the axis, and I will keep this as a global attribute now, just so we can see. So it's actually going to export it, and we can see what this attribute, what this axis is. We're going to do a cross product between a normalized v at direction and normalized v at down. By the way, when you're writing code, you can see here it's gonna do, we'll make it bigger. When you here, you can see this bracket, this green dotted bracket around. It's just gonna tell you where you are closing your code, all right? Okay, so we have that. Let's actually check our axis here. I feel it's gonna be the axis. And it's not working because axis cross normalized direction. Let's investigate this. So we're doing a cross between normalized direction . Huh, this should work. No, it does work. It just needed a quick refresh. Yeah, because I was going crazy looking at this and it should be working. I thought that I forgot to do this, where if you actually do this, it's not going to work because it doesn't know what what type it is, you know, because then the code doesn't know if it's a float or is it an integer, what is it? So it's a vector. All right, so we're going to be rotating around this axis. That's going to be our first axis that we're going to be rotating around. So now that we know how this looks, I will just put this into a local axis like that. I'm going to do another one. Rand axis, and that's going to be sample. I'm going to get it this time, I swear. Directional, uniform, and it's a random based on the PT none. Just close it. So if you guys want to know how that works, looks like that. So it's just random vectors, and each of them is going to be, the rotation is going to be different per piece because they're so random. So I won't be doing this that much anymore because I get a feeling that people are going to be mad at me if I continue doing it. So that's how I check what is this doing, is I write it out and then I create a marker for it. And for masks, I usually write them into color, so I quickly can see what that is doing. All right. So we have that. Now we have to create two random angles. So float angle equals an angle, so just like before, and a random angle, which is going to be pretty much the same thing. All right, so we have that. Now we want to rotate our matrix. So M based on the angle and the axis that we created. And we want to set the primintrinsic. So it's 0, if I remember correctly. Transform, oh my god. Transform the point number. We have the matrix and we set it. And we need our angle, and voila, we have something. Now you can see if we set this to 1, this is going to rotate quite a lot, actually by 180 degrees. If we set it to 2, it's going to do a 360 because this is right now in radians, and 2 pi radians is going to be 360. 1 pi radians is 180. So if you want to read this as normal angles or degrees, we need to say radians and transform this into, so that's how it's gonna say, okay, so these are radians, and it will give us angles. So now if you see, if we put this to 1, it's only going to rotate by 1, and that just gives us more control. So now if we go 80, we get 80 degrees, but let's set it to 40 for now. And what do we have? So we have this, we have our rotations, but we do want to create a mask. And if you remember, we created that mask center, right? So in theory, we can just say this and mask center, and this will work. So if you remember, our mask center is pretty much, we had it here, right? Somewhere. That's our mask center. So it's gonna multiply the rotation based on this gradient, which is generally what we want, but we want to change it up just a bit. So I will remove this here, and we will create 2 different offsets. One is going to be called animation, and the other one is going to be called fall off. So float anim, and let me just write this and I will explain what it does in a second. So ramp, we're gonna call it anim ramp, and it's gonna be based on this fit frame. So it's gonna move, and then we need what frames do we want to move this between, and between 0 and 1 because it's a ramp. All right, so what is this doing? Again, it's usually the best if we visualize it. I'm just gonna put this to smooth, no, steps, linear, hill, round. So I want this to be quite. So we are setting our frame, and frame, remember, is going to be dependent on this frame. So we're actually using our timeline here. And if we want to quickly check what this is doing, we can put it into CD. Yeah, that's not how we do it. CD. So you can see at frame 20, it's going to be at 0. We're going to continue, and it's going to go up super fast because at frame 21, it has to be at 1. But because we're controlling it with this ramp, it's going to go very slowly, and then it's going to pop and it's going to explode. So maybe it's a bit too fast, but put it to 20 or 30. So here you can set these as channels as start frame and end frame. In this case, I'll just leave it so I don't have to type everything out. But that's what that is doing. So let's put it back to float anim. And now we need to create our fall off, which is going to be based on that mask center. Fall off, another ramp. We can call it just fall off. Again, fit, but this time we're going to be fitting between, we're going to be using mask center, and I will be fitting between anim and 1 and 0 and 1. So this fall off is going to be animated, and our mask is going to get animated based on this. This is our min value, and this is our max value. So remember, this value is going to be 0 at frame 20, and then 1 at frame 1. All right. And then we are fitting that between 0 and 1, so we can use it in our ramp. So this is our ramp. And what is that going to do? Well, if we use this fall off now and actually multiply this, you'll see. Oh, and I think we need to actually invert it. So it's between 1 and, oops, I keep changing the scale here. No, that was correct. Oh yeah, I know what the problem is. So the first thing is this ramp here. We need to push it way back. So it actually is not rotating anything on the edges, like so. And the second thing is we need to expand the frame range between, let's say, 0 and 50. And that, we go in the beginning, we still see some of that cracking happening. So that just tells me we need to push this a bit more in. There we go. And now it's gonna open from the beginning like that. Cool, so that's what we wanted. Let me try to finesse that a bit even more. Cool. Yeah, that works. All right, so the next thing we want to add even more rotation. So I will essentially copy this rotation, on the rotate the matrix, and that's why we created those rand angle and rand axis. Great. And they also need to be multiplied by the fall off. So rand angle now controls the randomized rotation. So it's, before it was quite uniform. You can kind of spot how it's rotating, and now we're just gonna just randomize it a bit so you cannot spot the rotation anymore. And you can see, especially on these pieces, it's gonna be adding just a bit of randomization, and I think that's gonna be enough. All right, cool. So that's pretty much it. The only thing that is missing right now is how much it's being pushed inside, because the force is pushing inside the moon. And for that, we can just say V at P plus equals, and we want to use a vector, and that vector is our down vector because it's coming from the normals. So we're going to say V at down. Cool. So that's pushing everything out, and we want the invert of that. So we're going to be multiplying this by -1. And that's going to give us should give us the invert. Okay, and let me multiply this by, I don't know, 8. All right, so that we inverted the vector and multiplied it by 8, and now everything is going inside. But so for this to work, we also need to use our fall off. So we're still using the same mask, and you can see it's going to push everything inside based on that mask, and that's all working quite nice and dandy. I think this needs to be a bit less. And yeah, I think that works. We can still manipulate the mask with our fall off here. Do something like that, and then you can, you can change specific areas if you want to, but I feel like in this case, this works quite well. Maybe we need a bit more rotation here. Maybe something like that. But yeah, that's pretty much what we had before. If we look at this guy, and this, oh, that's not good. So this and this, yeah, it's pretty similar. I think in the other one I was not adding any of these, so it's a bit more, it's even more subtle. Maybe even push it more here, and less, even less push. Doesn't really matter. Something like that. But yeah, that's the whole code for this. So let's continue after all of this. I'm not sure what was happening here. Oh, yes. So here we were computing the velocity because this is actually moving. It does create a velocity vector for us. And when we unpack everything, we want to transfer that velocity. We can check how that velocity looks like here. And it's actually a very cool vector that's being created that is very cool for creating any kind of impacts. See that? I feel like it looks so cool. It has that very cool natural stepping, and yeah, it's very impactful. You can almost see how this could be used. It almost looks like an engine, and this almost looks like a spaceship now, and an engine just propelling it forward. So yeah, this it gives us a very cool vector just by computing that. So if you remember here, we were poly extruding this whole planet, and if we go down, we're merging everything, caching it, outputting it here, and then I was time shifting just by 12 frames, so everything was matching in the end, but I was doing that at the very end. And also you can compute the normals, so you don't see that edge anymore. You can see we still see the edge just a bit, but that's pretty much probably invisible in the render, so don't worry about it. If it is visible, then just double check if you have any intersecting geometries, but it should be pretty much invisible. Or maybe your mask is too wide, so it's actually moving some of these pieces here. All right, but that's it for the FXRBD Moon. So next stop is going to be the secondary particle effects. All right, so let's go into the RBD secondary now. So this is just going to be a particle sim, and we're going to copy some points onto it and just add some fake rotation with that quaternion technique that we did before. What we're doing here is essentially it's a simple setup, but it has some tricks. So we're importing the moon. We are splitting the moon based on our mask center like we did before, caching it, enumerating, creating the ID. This would be the same as doing ID equals ptnum in a wrangle, creating an add here. What you can also do is scatter on the geometry, and this would give you a more randomized result, but then you have to do the ID like that. So after the scatter, otherwise your ID would, because you would be creating new points and then your ID would not work anymore. We have an add here that we're deleting the geometry, keeping the points. And now we're doing this speed culling here. So we are culling based on the speed, and I can quickly show you what that is actually doing. It's a handy way of deleting points that are going too slow or too fast. So what we are doing here is putting a speed attribute, and we want to calculate the length of our v, and this will give us a float value that I usually call it speed. That's how I remember what it does. And if you put this into color, you can see that's how fast these pieces were moving compared to these pieces that are not moving at all. So now we just need to determine, based on a threshold, if you're moving too slow, you just get deleted, right? And you can say, you can do an if block. So if speed is moving too slow based on this threshold, remove the points from ourselves based on that ID point that we did. Here we go. So we're removing everything that is moving too slow. But we also want to remove everything that is in the center. So we need to get that center to actually become dark like this. So if the values are going to be low, it's going to remove that center as well. So we can just refit our speed. Fit speed between min and max between 0 and 1, because we're going to put this into a ramp as well. So now we have a 0, just so we can carve it even more to our liking. And now we can put another speed equals ch ramp, speed ramp based on speed. So this is grabbing this speed and we are writing into our new speed with this, okay? So this now gives us full control to carve everything, and we can just say that middle is actually, you can see we're changing the color, it's becoming darker until it hits our threshold here. And once it does, it's just going to disappear. So this, we can create like a nice ramp like this. And we're going to get like that. So we want this to be actually coming kind of from the center, expanding outwards, and then disappearing. So it's not disappearing completely because the speed values are still kind of here, and then you can see it kind of goes inside somehow. So what you can do here is once you get that animation, so this, you can just say, well, actually this is very high. And now it's gonna remove everything. And you can also do this here a bit. Maybe a bit faster, because we only need it for 3 to 4 frames to emit. So you just so we create that shockwave. Yeah, something like that. So that's what I had here. You can see it's only for a few frames. Now, another way of removing the particles, if you don't call it like that, you know, like we did here, this is just as a pro tip. You can also use something called ID to point or find attribute val count. And so what you do is you have this geometry, you go 1 frame into the future, or actually, sorry, 1 frame behind. Let me go a few frames back so we can see what's happening. So we are in the past, and this is the future. And what you can say is, if you find from here, you can see that this has more points here, this has less, but you can say which points are sharing the same attribute between these two. And that attribute is the ID. If you share that attribute, return a value, otherwise return -1. So we look up the ID, our ID, based on this input, and we get ID PT is the attribute, and see all of the points that are bigger. So all of this on the outer side does not exist on this frame, which means that this guy is going to say, well, I don't know what that is, so it's going to return -1. So then you can say if this attribute is not -1 or is -1, is gonna either invert this. Yeah, we're gonna be inverting that selection. But you can see if we say it's not -1, it's gonna give us that outer edge again. And this attribute does the same thing, but it just returns a different number, but it's gonna work the same. I'll leave this here on the side. All right, so we have our speed ramp. We just noise it up, nothing special, just a simple attribute noise here. Cache it. Now we need to shape our velocities. So do you remember I was saying that we're going to be using we're going to be using this vector, the directional vector that we did, and here we have our velocity. So let's quickly check what they do. So this is the velocity of a vector. So everything is kind of flowing forward like that. Actually, we need to check it here before we do anything to it. So everything is going backwards because our geometry, if you remember, we were pushing it backwards, right? And our directional vector is pointing inside or outside. If you remember, you know, you could have, it depends on how you did that cross product. It's going to either go inside or outside. So we are shaping it here and putting everything into vel, and we are just lerping between the two. And what I had to do is I had to invert both of them. So the velocity, so it's actually so here, this is our velocity. We want it to move the other way. So v at v multiply equals -1. And that's going to invert our velocity. Now I just wanted that to be a bit bigger, so you can just multiply it here by 20, or I don't know how much I used. Let's say 12. All right, so then we have that third vector. v at there, yeah, like equals -1, and let's just see what that gives us. So you can see before it was going inwards, now it's going outwards. So that's cool. And I think I did multiply it again by something. And now I'm lerping between the two. So lerp, which lerp is just mixing between the two values. So we're lerping between v at v and v at there. And we have to specify the amount. So if we say 0.5, it's gonna lerp 50% between the two. And we need to say this is at v. And let's check our v. There we go. So now we're kind of in between, but in order to, you know, do this a bit better, you kind of have to create this slider to actually see what's happening. And now you can see we're lerping between the two. So what I wanted is my particles to kind of go outwards, but just a bit forward as well, as you can see here. So that's how we shaped our velocity. I added a point val right underneath and added, so you say keep incoming. You don't set a value, you keep incoming, and then you add some kernel noise just to add even more breakups. And I added even more breakups here in this section. So after you have your geometry, I usually create this in a VOP because if you're dealing with noises, it's just easier. So we have this. Let's create a turbulent noise and put this here. Back to the color, remove our velocities, and 1D. So you can see these are the values we're going to be working with. So everything that's white is going to leave a spike in the vector. Everything that's black is going to be negative. So if we multiply our velocity with this map, we're going to get this. So you can see this was white, so it's pointing up. And this is actually -1, so it's going inside, which is kind of cool because sometimes you do want some more resistance from the particles. You don't want it to just be at 0. You kind of want to add resistance so the particles actually move against all the other velocities. It works sometimes, but it totally depends on your effect. All right, so what we need to do now is we need to fit range this. So we said this goes between 0, 1, and 1. And you can see it creates a nice little spiky thing that we kind of had before, but now it's even more exaggerated. Now we can put it through a ramp. Just call it something, doesn't really matter because it's only one ramp. So we have created a ramp outside. And now you can kind of control how you want this to look. You can see everything that is super white is going to be pushing through now, but you kind of want to have a good mix of things. And that's how you create even more control with your velocities. And it's a very simple technique that works super well. If you want some of that negativity back, you just have to create another fit. Go inside. So our ramp right now is between 0 and 1, and you just want to maybe add some negativity. So you can see it goes into the minus quite a lot if you push it too much, but if you just say like 0, 1, it's gonna just add some resistance. So that's how that was created. Was I multiplying it? Yes, so I was multiplying a bit towards the end just to get even more, but I kind of like these shapes even better. So that's what we had. And now we push everything into a popnet. In the popnet, we're not doing anything super special. What I'm doing is importing everything. We're doing a pop wrangle to add even more directionality. I can show you. Set this to 50. everything's going to be pushing outwards even more. We have, of course, a pop drag with a random air resist, and here I was putting air resist, plusing it with the age, so everything actually stops. Almost everything stops at the end. We still have some particles that are kind of moving. All right, so let's do it. Let's do it here in a fresh popnet. All right, so let's make some more space here. The first thing we're going to do is make this actually imitable. So we're going to say points. So even just from this, we get a very cool result with our velocities, but everything is just moving infinitely, and we do want more points. All right, so this looks pretty cool, but we can shape it even more. So we're gonna add a pop drag, and I like using pop drag. It just gives it more weight and more believability, but you can see this just stops everything, and that's not what we want. So we want to use this expression here. I kind of wish they were add this here, or you can add it if you want. But so air resistance, we can say see the parameter is called air resist. So we can just say air resist equals a 0. Let's see if that even works. Great, so it does work. So air resist is 0, so we can now give it, let's say, something similar that we did with that noise just a second ago. So we can say, let's do a rand based on the ID. So this will give us a random value between 0 and 1 based on the ID. So some particles will now have air resist of 0, and some of them have air resist of 1. And you can see that gives us a nice mixture already. If you want, you can fit 0, 1. This between 0.2 and 0.8. Need a comma here. And that works. And if you want even more control, you can put this into a ramp. So now it doesn't work. Create a ramp. And what I usually do for these is just like this zigzaggy pattern. So some of them have this, some of them don't. And yeah, kind of works. Maybe the air resistance needs to be a bit bigger on the lower end, just so they don't fly off like that. Maybe don't put this to 0 as well, because everybody needs some air resist, even the ones that don't have a lot of it. So yeah, put this back. What we can also do is increase our velocity intake. That didn't change it. So you can see now we have a more punchy explosion in the beginning. Probably even more, right? 8. It didn't reset. So if it doesn't reset, you just have to kill this and put it back online. You do it with the hotkey with the Q. But yeah, this feels pretty good. So pretty much I would just leave it at that. I wouldn't do any of the other stuff I did in the other walk, but we can quickly check what I did. So I added an additional pop force, and this is our pop drag. And this pop wrangle we're using that directional force that we get from here. If you remember, we have that direction vector. So we're doing the same thing here. So V at force is something that happens in a pop. It's a you create a pop wop, you have a force here and a velocity. So that's something that is being recognized by the pop solver, and this will push everything out. It's like this pop force. It's also using this force velocity force attribute to, to add just this movement to your sim. Now here I also did a geometry wrangle, which I probably wouldn't do anymore, but it was just plussing it with the age. So over time, everything stops. Well, over time, everything should stop. More or less, you can see we only have a few particles that are kind of flying outwards, and that's, I think, because of this force. So yeah, the force is just pushing, forcing everything to just still move outwards just a bit. So, but I don't like how everything else stops, but for this effect, it was looking fine. And then the only other thing that I have is a pop replicate that stops replicating everything. So you can see this is without the pop replicate, and this is with pop replicate. And it just replicates, it creates almost like a trail of particles, like some clumping is occurring. You can see from here, we're getting some clumping, and I'm just saying if $f is bigger than 35, don't do anything. If it's not bigger than 35, then emit by 4. So this will just create a if, like a very fast if statement. You can see it goes between 4 and then it stops emitting. And then here I'm inheriting velocity. Maybe this could be even a bit higher. Yeah, I like that more. You can see how we're getting those clumps. And I think this should be less. So I will multiply down my age. So now, oh yeah, look at that. But now probably this effect is becoming too big, but I like it. It looks very cool. This can be used for multiple other things. So after I do that, I do a second one, and this one just has, I'm emitting less particles from the beginning. It's the same setup. It's exactly the same. The only thing is I'm only birthing here 900 particles, and I believe here I'm adding a bit more. See, I'm spawning 20, so I create more clumps like that. And then I just merge the two, and that's what we get, which is pretty cool. So I have a cache here, so you can see it was just a bit smaller because we added, we removed that age. And then here I'm randomizing the p-scale. So this whole block is about taking the particles, p-scale, and then copying this to the geometry. Copying our platonic to the geometry. All right, so that's what we get in the end, which I feel is quite cool. The p-scale has a cool thing that we're using here, a custom ramp. I use this a lot just because it gives you this power curve. And with this, you can see everything here. And if you guys listen to any of my other tutorials or podcasts, I always talk about this Fibonacci sequence thing, or the golden rule, golden circle. It's something that you can use in composition, and not just in composition like a photography composition, but in composition with the ratio of scale. And what I mean by that is you can see we have a lot of small particles, and only 10% of the total amount of particles are going to be big, and that's this 10% or even less, right? Everything else is super small. So you can create that with this curve. So if you go to attribute randomize, without it, everything's going to look like this, which is horrible. So here you can say p-scale, and already you can, control the random p-scale, but that's not enough. You're just going to get maybe this, maybe if you really needed a lot of small ones, and then you could merge it with this again. So you would get twice the small particles. But what we really want is if we go to custom ramp here and you say fit 0.1. So the smallest one, just put it to 0.2 for now. And now you can refit this ramp. And make these smaller. And make this even more exaggerated. And these smaller. So like that. So only just like top, this is probably like 2% of them, even less, are being big. Everything else is super small. And that's going to help quite a lot with, you can see they're doing this cool clumping because of that pop replicate. That's it. And potentially you could still use this for other things like magical spells or any other effects, because it doesn't have to be used just as a shockwave kind of grain and dust pass, but you can see because it's expanding like that, it could be used for magical forces. The only other thing I forgot to mention was I added more rotation to our particles, because otherwise everything is just moving like that, which is not ideal. You could do some tricks in the particles to give them rotation, but I always like to control that after the sim. So you can see everything is rotating randomly based on that sample direction uniform, and angle is set to time. So angle is just like spinning all the time. Then we use a quaternion, put it into an orient. And like we discussed before, the orient is being picked up by the copy to points, as orient has the highest priority between, normals, vectors, and anything like that. If you put an orient, he's like in the top command. And that's it. That's how we did the RBD secondary. Now the only thing we have left is to do the smoke, the wave, and the flight path. All right, so let's jump into how we did the FX Smoke Center. Fairly simple and clean setup, super small. And that is partially due to this pyro burst source, which is super handy. Before, pretty much everybody had their own setup for creating something similar like this. And if you've been in our explosions for Houdini workshop, or if you saw the webinar I did, you can see that I pretty much had something very similar to this tool created. All right, so the pyro, this one is very straightforward to use, I feel. So you have the spread angle, you have the roundness, you can control the different shapes that you want from this, number of trailings, and so on and so forth. You can play around with it and check out all the different features. You can even change the start frame, your frame duration, so how long do you want this to be animated. You can see it's expanding outwards, and you can change the expansion here. So if you just say, well, no, I just want it to be like this, then it's just gonna pretty much appear. But you can then animate it, so you can have this really poppy and fast start to your explosion, or in this case, this middle smoke, spiky smoke sim. And you can see how fast it is, and that's partially due to, if you look at anime or anime, or in our case, the One Punch Man anime, you can see most of the effects are super poppy, which means that they're very fast and explosive like that. So this is set to 12 for that reason, so it's very fast. All right, so we bring out our trusty red dot that we've been using throughout the whole setup, copy it. This guy creates density and temperature, and also we get velocity forces coming from this. So then we do a volume rasterize attributes, just density and V. You can add some velocity blur to this if you would like. And if we see, if we go back a bit, so velocity blur will just blur based on that velocity attribute, and you can see it just creates a more clean lines, but it's up to you. I kind of like it when it's like that. Visibility, just to hide the velocity so I don't have to see it. And then we have our pyro solver, which is pretty much a stock pyro solver. I was not changing almost anything to this except this time scale. So the time scale starts with 2 here, and then it goes to 0.2. And that is because, again, you need to create that really fast expansion and then a stop, almost like a slow motion effect. So that's what we're doing here. The only other thing really that I'm adding is, okay, so sourcing only has density and velocity. And then under shapes, I'm just adding disturbance and turbulence. So nothing special, that's it. We cache that out, that's what we get. And the only other thing here, I was scaling everything down because if you look at it with our moon effects, center, it was just a bit too big. If you scale it, like in comparison to the other effects, it was just a bit too big. So what I did was I scaled it down. In order to scale this down, you just create a spare input here. Put the center here. And then you can say centroid -1, which is grabbing this spare input on X, Y, and Z. So 0, 1, and 2. And it's going to grab that centroid. And now we're scaling this based on that centroid. Otherwise, it would be just scaling in a world space, which is, disappears. All right. And then I'm time shifting it just so it starts a bit earlier. That's it. That's it. Smoke wave. All right, let's go into the FX smoke wave. So the setup has a bit more nodes, and I will show you how to create an even simpler version to that. This whole thing could be avoided, but I'm keeping it just for the sake of educational purposes. All right, let's bring in our RBD moon. I'm time shifting it. It doesn't have to do anything. We just need the inside and then scattering on top. All right, the next step is creating a mask that will serve as our smoke wave. And that's it. We are just transferring the color. So this is black and this is red, and then transferring the color. And then here we are. So first I am using that mask center to create an edge remove. So CD equals to this. So this, we create this ramp and then just remove everything from it. So let me just put this back, and I'm noising it up, and then I'm removing the points based on that color. So essentially I'm just saying this is all what we did before. That's why I'm going through it a bit faster, but I'm saying if the CD, I put it in CD. I know I shouldn't, it's a bad thing to do. But if CD is smaller than threshold, remove the points. So it's going to be removing it based on that color. And then we are shaping our velocities. That's also what we did before. So we have our outward, so we have our direction and down vectors. If you remember them, we can quickly show them. So oh yeah, so they should be showing up. Oh, here we go. So that's our direction, and this is our down. So down was that normal vector, and direction was pointing inwards. And what we did here is I created an outward and upward vectors, and then just put them into V, plus them together with, and each of them, they have a scale here. So they have a multiplier, and with that multiplier, I can also I'm inverting them if I want to. So you can see the outward scale was like that. And before we inverted it with multiplying it with -1, but you can also just multiply it with a channel. And in a channel, you can say -1, and that's going to invert it as well. But now you have the flexibility of multiplying it even more in that direction that you want to. And that way you can create almost like a lerp effect, but we are plussing them, so they are becoming bigger if you plus them too much. Just keep that in mind. But what I wanted was a vector that kind of goes backwards a bit, but so a bit backwards and not inside, but outside. And that gives us that, that velocity. All right, so let me back up a bit. I just wanted to show you what is happening here. And later we just put it into a pop network, and it's pretty much the same pop network we used in the other example. But let me back up and go and cover this point a bit. So like we said, we are creating just this mask, and we are creating it using this. And this guy is our wave that we created way back in the lesson on the moon. So I'm caching that out. I'm calculating the IDs, so each point becomes an ID. You can see on this one, some of the points are rotating just a bit. And that is just because we were raying it on the surface, and when we were blasting the geometry and then creating this primitive from it with the polyline. And you can see it's rotating a bit, and that will create problems for us later. Let me just show you what problems I'm talking about. So right now, here we go. Right now it's fixed, but if I haven't done this part, if I just skip this over, you can see it would be rotated a bit, and that would give us undesirable results. And that is because the thing is rotating. So now that with that fix, we pretty much get a perfect circle. So what am I doing here? So we have this, I have the circle. I am also creating a centroid based on get bbox center, just looking at myself and putting it into I center, and then in the transform, I can use that as a, and by the way, it's a detail. So if we go into our spreadsheet under details, we get that I center location just in the center. And then I'm using that detail I center to scale it up and down. And I'm scaling it down even more. And it's kind of doing a good job of scaling it. Again, if we didn't do this, it would be just going somewhere in the world transform. So we have that. The reason why I'm scaling it down even more is because I just wanted more coverage happening here when we're transferring that mask. All right, so then I'm doing a time shift here, so this one doesn't move, and I'm doing an xyzdists and a primUV function here to put it back into place. So you can see this was static, and now it's moving again. And what xyzdists and primUV are doing, xyzdists is kind of shooting rays and finding almost like that nearest point. But this will also return, in this case, it will write into this prim integer and a vector called uv, and we determined them. And now we can use those functions to fetch pretty much any attribute that we want from the second input. And in this case, we were fetching the position. And these go together quite well because this guy shoots the rays and this guy gets the data, essentially. And if you, again, you can go into help by pressing F1. So see, finds the distance from a position to the closest location on the surface geometry. So this gives us the distance as well, but it also, you can write into these attributes that you create. You can see there's a version where it doesn't write, it just gives you the distance. And there's a version where it does write, and you can see that end sign here. That means that it's going to write into these two attributes. And then you use the primUV, which is interpolates the value of an attribute at a certain parametric UV position. So it knows the position, the UV position that we gave it here from the first attribute, the first index, so 0, 1, and we are fetching the position from here. And then we're just saying our position on this time shifted one is the position that we got from the second guy. And that will give us our position back. But now that rotation is much more stable. It's not rotating anymore, as you can see. So that's a weird, not a weird, but it's like a hack. And yes, we could have just scaled a circle and rated to our moon. If you're wondering that, that is also a possibility. This is a very long workaround because we already created that, and we created this ring, and now we are just fixing some of the issues that we got with that ring. So yes, just doing a circle, raying it here, and scaling the circle would also be a very valid option to do. But yes, educational purposes, that's why we're doing this. All right, so we are raying it again because it was a bit out of place. After all of that shenanigans we were doing with this transform, it's just a bit out of place. So we are raying it again, but now it's not rotating and it's properly positioned. This retime is very important. It's not a retime, we are just using the interpolation. Everything else is set to its default. I'm not sure. Oh yes, so here I'm calculating the velocity. So we have a retime that is interpolating. I'm calculating the velocity because before we didn't have it. You can see here. And now I'm trailing this. And this will create like a cool little trail based on, you know, the velocity essentially. If I was not interpolating, this would not work properly. It would be interpolating kind of the wrong way. And that is because if we look at our time here, if we go to, well, this one actually is working now. This one was not working before, right? Oh yeah, so here we go. So you can see there is a bit of glitching happening here with the time. See how it's jumping, and that will not work on the trail because the trail needs like a perfect retiming. And with this, we are just interpolating back those frames. And now it's very smooth. And now the trail is going to work like it should because it knows it has a perfect interpolated position. I'm removing the geometry but keeping the points, and then I'm adding merging them back by this ID. That's why this ID here was very essential to create. And now we're going to go into a for loop, and I will do this one again. So we have our each named. So what we're doing in the for loop is just carving everything, so we get a more randomized result. And we're carving with this expression. So if we plug this in here and go set by for each primitive, for each primitive. So if we go to a single pass here, you see it's gonna just use each primitive, each connected line, and it's just gonna give that to us. So if we put down a carve and carve it, it's just gonna kind of erode it, right? So if we do that on all of them, that's what we get. But we don't wanna be doing this on uniformly on all of them. We wanna do it per primitive and kind of give it a random value. So what you can do is create this meta import node. And this will give us a attribute called iteration. So right now we have 100 iteration is on 150. If we put this to a single pass and go to 6, the iteration is going to be on 6. So this is essentially returning on which primitive we are looping through, right? Which means that if you can see it does it all at once, but it's actually going through them one by one. But we can use that iteration to throw it into a random and a fit. So I usually call this iter or whatever. So just so you know, it's an iteration. And then on the carve, we're going to create a spare input and just put this in. So you can see it creates this violet connection now. And now this pair input, we can call it with -1. So here we're going to say random, and we want to grab a detail attribute, detail. It's on -1. So on that iter, on this null here. And then we're going to say iteration. That's the attribute we're grabbing. And then on the 0 index. So that should give us this. And it works already, but for convenience sake, we can say 0, 1. And you say 0, 1 because you know this random value that we're inputting is between 0 and 1. So 0, 1, and we can say 0 and 0.8. There you go. So that will give us this result. And now I'm assembling them. So essentially packing them, doing a point jitter on all of them. So they're even more random, something like that. Unpacking, resampling. So they get more points in between because before they were like this. And then adding the color. And now we are transferring this here. I know, I told you, it's way overcomplicated for what it is. But now hopefully you know how to use these iterations in a loop. And maybe you are more familiar with how to use the xyzdists in the prim. If you're still wondering how all of this works, we're also going to link to some very cool documentation about these two functions with more examples. So you can go through them yourself. Again, just as practice. So for this, yes, what if we just took this damn ring, right? Actually, when it's right back, and we just did a copy transform. Just copy a bunch of them, scale it down. You can see it's scaling down, but it's going into this portal mode. That's because we need to pivot this. We need this pivot position, and now it's going to go where it should go, towards the pivot. And let's make more of them and do something like that. And now if we did a resample, put this to like, I don't know, 80, and noise it based on position, we're gonna say 0 center, something like that. Bam. And let's color it with a, oh my goodness, red. Plug it here. Done. And this would kind of work as well. And it was way more simple. And we can, if you want it to be deeper, you can just push this, and this will kind of control how deep, it's going. Essentially the thickness of it. All right, cool. Let's move on now that we got that out of the way. This we kind of, I went through this. So I'm creating another attribute called add remove based on that mask center, blasting everything, adding some additional noise, removing the points based on that threshold, based on the color, shaping the velocity, adding some curl noise to our velocity. So you can see what that is doing. And then pushing everything into a popnet. This popnet is the same setup as we had before. It has a pop force and a pop track with a random air resist. And that will give us this result. And you can see we're getting some very cool clumping happening here. And that also helps with the randomization of how the smoke is being not detected by, but just spawned from our density value. I'm trailing here just to create some just so I create more particles, and then putting it into a pyro source, we are creating velocity and density, rasterizing everything. Then I animate the density and velocity. By animating, I just mean I multiply them all down. So the actual emission is only happening for just a few seconds, and then it dies off. In here, I have the collider. It's just a cap that we, our RBD cap, getting some detail, time shifting it. RBD, this is not super necessary, but it just creates more simple shapes for the collider. And then I'm using a VDB from polygons, calling it collision. So our pyro knows that this is a collision volume. This is pretty much a stock pyro. Again, the only thing that I'm doing is changing the time scale, which I'm animating from 3 to 0.2. Sourcing, this is all basically just velocity and density, because those are the only two that we have. I'm not using the speed field. And on the shape, I'm just using disturbance, turbulence, and shredding without that speed field, just on the density, because everything happens so fast and it gets slowed down so fast, it was not really necessary. And it's this is very cool. You can see this in Houdini 19, you get this smoke ambient occlusion visualization on the smoke, so you can see all the detail. I would say I went a bit too heavy with disturbance, but it was looking cool. So after I cache this, that's what we get. Time shifted to get it to get everything in with the right timing with the other elements, and that's it. The only other one that is left now is the FX Center flight path. So let's get into this one as well. And you remember we created this line way back in the setup. Here we go. It's here. And this had a curve view attribute, which is that attribute that gives you a 0 to 1 mask on your curve. That is very useful to create multiple things. So we use that to create the width of this trail, and now we're going to use it to create a bunch of noise masks as well. So I create another mask that you can visualize here, just to remap it. So that's how it looks, just very tight in the beginning. I create a VDB from polygons, just create density and create this noise mask. So this is the noise mask, and you can turn it into a volume. And then I just remove it from the visibility. There's a bunch of noise volume pops that are happening here. So this is noising up the whole volume. And this one is noising up, you can see, just the beginning. Just because it was a bit too clean in the beginning, I created another mask and just noise that one up as well. So how does this work is, if we do a VDB active, this essentially just creates a wider bounding box around our smoke. It just gives it more padding. If you go to expand and you expand the voxels, let's create a volume bob, and here we're gonna create a let's do an flow noise. Put it into position. And now in order to noise this up, and let's actually see what we're working on. In order to noise this up, we need to create a volume sample. So this will sample the position on our primitive volume, which is density. And it's on the first input, and plug this here. And you can now, just like you would on a geometry, add and noise up the position of those voxels. And this will give you a noised up a noised up volume. And what we can do now is, if you only want this to be noised up at the beginning, we can bind that mask, which was called Yep, just get it here, noise mask, because we have that in our as a volume right now, and it's a float. And now you can just multiply that as a mask here, and it will only do the noising in just in the beginning based on that mask. So if we do it longer mask, it will do everything except the tip right now here. So that's how this was done. And then it was time shifted again to fit with all the other effects. And if we quickly display them, I think it looks quite cool, especially with this ambient occlusion visualization. In some cases, you almost don't need the light, but if we enable the light, it looks even better. So that's how all the effects look like. And then you can put in the moon. The moon is a bit slow to preview, but I think it looks quite cool. It doesn't have that extra detail that we would get from the additional, where was it? Interior. But for a final rendering, I would definitely turn that on. And then we have this, and it looks pretty cool, I think. And it works quite well. I think we still have that preview here. There we go. With all the effects turned on. The only thing left now that I won't do, but I encourage you guys to do, is that camera that you see in the One Punch Man, and the camera that Jesse did as well, because that camera actually creates a lot of punch, even more punch than we already have. So our effect is quite punchy because it goes fast and then it slows down. But if you can emphasize that with camera shake and with that zoom out, and it will feel like everything is happening even faster, because while we are zooming out, we get motion blur and we don't see exactly what's happening. And with that motion blur and camera shake, it will feel like this was an even more explosive blast that it already is. All right, everybody, we came to the end of this tutorial. It was quite a long one. I hope you enjoyed it. Let us know in the comments if you like these type of tutorials, and we're gonna do our best to do even more of them. So, all right, happy learning and good luck. Bye.